Okay,
on hashes.
lambda is 0, so you just need the data penalty is minimax.
Okay, so it's lambda 0, then our original equations look like that. Okay. So d epsilon em equal to 0. That says the solution, if we're starting at some point like this, I'd like to find a new point where the gradient is 0 in all, in this case, 2 directions. It's going to give us a set of equations like this. Okay, so you solve for the system of equations. And that guy is going to be, and by the argument we had before about the linearity of this system, we can do that. And so this delta m points towards the area where the derivative is 0 in all directions. And that's the only place where that's true, at the center of the bullseye. Okay? Yeah.
Does lambda correspond to something? Like a physical?
Marco, does lambda correspond to something?
No, yes, it's like in a Bayesian framework is the a priori knowledge that you have on the parameters.
You
But
make
no,
it complicated like that.
no physical, it is not a physical.
Because my question is that why there are halves in the equation. If lambda is arbitrary, you can just...
Lambda is arbitrary.
Yeah, then
Context.
like, why is it half lambda? Like half if it's arbitrary.
Because it makes things easy algebraically. You don't carry the half over here when you take a derivative. That's kind of right.
Oh, I see.
This is 2 m's here, right? You bring down to 2 and take the derivative. So it just makes things easier algebraically. Yeah, you don't need to put a half there. But this, let me provide the answer. It's up to you what lambda is, the value of it. If it's large, then you're emphasizing I'm more concerned about having something close to the origin than I am in trying to reduce the data misfit. And as it turns out in practice, with some kind of gradient descent approach, they have large lambda at first because you want to be in the vicinity of where you think is a reasonable solution near the origin. So lambda is going to be large. And as the iterations proceed, there's an empirical way of determining how to reduce lambda as the iterations proceed. So at some point, you're here, and then lambda is going to be a very small value when you're close enough to what you think is a good data misfit. You never wait till you get data misfit equal to 0y, Marco, on new iterations. You don't want your data misfit to 0y.
To misfit 0. So can you repeat it?
Can your data misfit ever be 0 in a real live geophysical problem?
No.
No. So you're never going to wait till it gets to 0. You're never going to wait till it gets all the way to here. You're probably going to be happy somewhere along this inner bullseye. What you mean by inner bullseye, that's up to you. You can actually calculate that. Like if you are doing travel time tomography, you pick travel times and millions of traces, and you can estimate what the travel time area is, the average travel time area, the variance of that travel time area. And that's going to determine what your RMS residual data predicted minus observed data areas. So there's a quick and dirty way of estimating when you should stop on your iterations. Yeah. Any other questions? Okay, so that's the answer that you gave us. It points there. And so then I have the question, well, what if lambda is not pretty big, and what happens if it's between this end member and that end member? Say some intermediate value of lambda. Where does that delta m point? Marco?
The,
Delta m points here for
in the middle, like.
yeah, somewhere in between. Okay. You know, it's going to smoothly go between this guy and that guy, smoothly because it's a linear function of lambda. Okay. Okay, let me give you a more concrete example of the ill-conditioned sets of equations. Let's set up these two simple equations here. This is our L, this is our M, this is our D. Okay? And the context is, say, some kind of travel time tomography with these symbols. And I think there's a linear fit between the observed data and the predicted data on the left-hand side. Well, then I go ahead and form this, and when I form this, I get the what we're going to call the Hessian, X transpose X. And notice that X transpose times X is what? It's going to turn the black A to the 1/2 into just A. And it's going to turn the red B to the 1/2 into B's. Then you go carry out the algebra here, multiplying this matrix times that, and then multiplying the resulting vector by this transpose vector, this row vector. You get that. So this is a quadratic polynomial. And if I were to plot that in W1 versus W2 space, I call it WX. I'd get a series of contours like that. The series of contours, if A is equal to 1 and B is equal to something that's very small, my contours would be such that it would be very elongated in this direction. Why? After the Why aren't the contours elongated in that direction?
Because you give x1 or wx a larger weight than, is it that? Because wx has a factor of 1 and wy has a factor of 0.1.
Ooh. It's like saying the cat is a cat because it's a cat. The animal is a cat because it's a cat. Anybody have a little bit more illuminating explanation of why the contours? I could have. What if I had put the contours like that with this kind of equation here?
Because basically it's close to 0, the 0.1.
Yeah.
So like it's counted little.
Yeah, this hardly counts at all. So you can make many different models that kind of give you about the same misfit error, because this coefficient is so much smaller than this coefficient. On the other hand, if you try to change the model in this direction, quickly the epsilon, you have to visualize, there's a big air ball here. The errors really start zooming out, as getting to be big as you move modest amounts in this direction. Because this guy is a pretty large number, the coefficient is pretty large. Well, there's a thing called a condition number, and one of the definitions of a condition number is that the ratio of the largest absolute value, the largest eigenvalue over the smallest eigenvalue. By eigenvalues, I mean the eigenvalue associated with X transpose X here. I don't think I need to tell anybody what the eigenvalue is. So if A is much bigger than B, then that condition number, lambda max over lambda min absolute value, is going to be much larger than 0, and that's another indicator. Not just the geometry of this guy is an indicator of poorly conditioned system equation, but there's a scalar metric that also tells us we're in trouble with our system of equations. That has many almost possible solutions that satisfy our system equation. And if one of the lambdas is 0, then that means that the contours, they're almost, well, they're parallel in one of the directions. So infinite number of possible solutions, meaning a non-unique system, non-unique solution. Fortunately, if we somehow could massage the system of equations to go from this to that, then we round out our contours, which is a good thing. Then we have a chance of making things happen. Is there a way in which one could have taken our original system of equations and rounded out our contours to give a much better system of equations that is more well-conditioned? Is there something we could have done with our original system of equations so that our x transpose x, which determines our gradient directions, the contours will look like something round rather than elongated? Okay, well, you can't see that right away. Let's see what we can do. Now, what's a bad conditional number? Well, anything greater than, I've seen in the literature, 10 to the 5th is a bad conditional number. I say, let's be conservative, 10 to the 4th. So let's see what we can do to fix this problem up. And this is important for neural networks, because unless you pay attention to what you're doing, you're going to have an ill-conditioned set of equations. Or if you don't understand the basics behind optimization theory, you're going to be in trouble. Now, somebody at my DL lecture asked me at the end, well, you know, we tried neural networks on, you know, this data, and it worked okay, but then we put in more data, it fell apart. Could have been many causes for that. And one of the causes could be what I'm going to talk about now. So here's our original system of equations, x, w, equal to t. I'll set it up like that. And you'll find out later that I usually, for a vector, I put a small lowercase w. You'll find out later, neural networks, really what you're trying to invert for is a big matrix of w's. Okay. So I might as well get you used to that notation. Neural networks will have some kind of matrix multiplication like that. And for our simple case of diagonal components, we just have this set of diagonal components. You go ahead and do the x transpose x in general for a lot of these guys. You're going to get diagonal matrix back again for x transpose x. And this is our w, and this is our t. I should put an x there. X transpose is nothing here. So, here's a problem. If you have two types of input, each one of these guys is an equation. Remember my talk Wednesday? One equation was a picture of a cat. Okay. That led to, say, one dot product between one neuron and the weights associated with the neurons and the flattened vector associated with the cat. Then you did it again. And another dot product. You keep doing that. So you get all these input vectors associated with different cats. But it turns out your very last picture in your training set is a dog picture. Okay. Well, a dog picture might have different units than the cat pictures. For example, the cat pictures are always taken during the day. Nothing but really big numbers. 255, 240, 220, whereas the only dog picture I have was taken late at night. And so most of the intensity values for the dog pictures were what? What values? Abdullah?
Value for night,
Yeah, take a dark dog picture.
That would be small or different than.
Give me a number.
Okay.
A range of numbers.
Say from 1 to 50.
50? Nah, that's too
I mean,
big. 1 to 20, 1 to 10.
Okay.
So this really had a very small number associated with it compared to the numbers associated with these guys. And you notice in my talk about the input, another example I gave was for different, I put in a seismic image and I said, no, that's not good enough. We need other images that have features from the seismic image, like dip angle. Another picture was intensity. Another picture was frequency, highest frequency contact, da 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 da. Those all have different units. So that could also lead to an imbalance of numbers when you compare the numbers along this last row to the numbers on the other row. So there's a real problem